So we want to look at factoring a difference of squares. So why this might be different from factoring a trinomial is you see that we have no middle term. So when does this happen? Well, we're going to just take a look real quick at a problem that's going to kind of illustrate when we see something like a difference of two squares, but we're going to take a look first from a multiplying binomial standpoint. So if we have two binomials, let's say we have x minus 2 and we have x plus 2. If I go ahead and multiply those together, so we can use double distribute here, so we'll have x squared plus 2x, and then distribute the second one, minus 2x minus 4. When we combine these middle terms here, right, they add to 0, and we're left with just x squared minus 4. The two terms that we're left with, x squared, we got by taking x times x, which is what makes that a perfect square. And the last term we got by taking basically 2 times 2, but we had a negative there. And 2 times 2 is 4. 4 is a perfect square as well. So the only difference there is that we had a sign for a negative, but 4 really is our perfect square. Okay, so we're looking for, when we're going to be factoring this way, we're basically looking for binomials where our first term and our second term are perfect squares, and we have a difference in the middle, right? Because when we started, we needed one negative and one positive of those numbers so that in the middle we got this canceling because one was negative and one was positive. Okay, so the rule for difference of two squares when we're factoring is we're going to factor it into two binomials. The first term in each binomial is going to be the square root of the first term in our original problem. So if this was a squared, we got this by taking, oops, sorry, that zoomed out for you. We got a squared by taking a times a. So the square root of a squared is just a. So that's going to be the first term in each of these. We got b squared by taking b times b, but remember, we needed one positive and one negative in order to get the middle term to cancel out, like we did in our distribution problem there. Okay, so we're going to be doing this where we do have some values, not always just numbers. So let's take a look at some of those. So it's always kind of helpful to write above what did you multiply to get your perfect square. So for x squared, we're always going to have multiplied an x times an x, but for the other numbers, we're going to have some difference, right? But for 16, we would have multiplied a 4 times a 4. So now when I go to factor, my first term, I know I needed an x times an x to get that x squared. Then I know I need one positive, one negative, so that my middle terms are opposites of each other and they'll cancel when we combine them. And then for the last one, I know I needed a 4 times a 4 to get a 16. Just like in all of our other factorings, we can check by distributing back out to make sure this works. So x times x gives us x squared. X times negative 4, we're going to have a minus 4x. 4 times x plus 4x. 4 times negative 4 minus 16. We can see our middle two terms are going to cancel to 0 and leave us with an x squared minus 16, which is what we had started with, so we know we factored it correctly. Let's do a couple more of these. So to get an a squared, we would have multiplied a times a. To get 144, we would have multiplied 12 times 12. So now we want to break it up into our two binomials. All right? So we would have an a in the first place, first term, 12 for the second term, one positive, one negative, so that we would get our middle terms to cancel out. Okay, so what happens if we also have a leading coefficient that's not 1? So let's take a look at that now. So to get the x squared, we know we multiplied an x times an x, but what about to get the 4? Well, first off, we want to check, is 4 a perfect square? It is. So we're good to go as per usual. So we're just going to say, all right, well, to get that 4, I needed a 2 times a 2. So we would get 2x times 2x would give us 4x squared. 25 is 5 times 5. And we can split this up like usual, except now our first term is going to have a coefficient with it. So we're going to have 2x and 2x in our first place, 5 and 5. And then to get that middle term canceling when we distribute, we need one positive, one negative. Okay, why don't we check this one just to make sure since it's a little bit different. All right, so we're going to distribute 2x times 2x does in fact give us a 4x squared. 2x times negative 5 is minus 10x. 5 times 2x, we're going to get plus 10x. 5 times negative 5 is a negative 25. Our middle two terms are inverses, or opposites, we sometimes say, right? One's negative, one's positive. So when we combine them, they'll cancel to 0. We'll be left with our 4x squared minus, oops, I wrote 22, I meant 25 there. So we're good. We did it correctly. All right. So sometimes we will have multiple variables, and that's okay as long as, again, everybody's a perfect square. So looking at this first term, for 16, I would need a 4 times a 4. To get x squared, I would need an x times an x. So when I go to factor, that's going to tell me my first term of each of my factors, 4x and 4x. Now we're going to look at the second term. Well, 49 is just 7 times 7. Y squared is just y times y. So to get that second term, we would have had to have multiplied 7y times 7y. So that's going to be our second term, 7y. All right, we still need opposites in the middle, right? One positive, one negative, so that we get the cancellation in the middle. So again, a little bit different. Let's check this out. All right, so distributing. 4x times 4x, that's 16x squared. 4x times negative 7y. This is where things get a little more interesting. But they're not too terribly different, right? So 4 times negative 7, we're going to get that minus 28. And then you just want to think x times y. We can't simplify that much, so we just leave it as x times y in our term there. Okay, distributing the second one. So now we have a positive 28yx, and then distributing the last piece here, minus 49y squared. So what you want to remember is that multiplication is commutative. So I can rewrite this term here as 28xy. And then we can see that the middle two terms are opposites of each other. So they're going to cancel to 0. And we're going to be left with our 16x squared minus 49y squared. So I can confirm, yep, I factored correctly because then when I distributed again, I got what I started with. So let's check out number 5. Okay, so one thing, and I think we mentioned this at the beginning, but I'm just going to mention it again. Make sure that this is a difference of squares, right? Difference of squares. So we need to be dealing with subtraction, right? Addition won't work because a positive times to get a positive for that last term, we would have had to have multiplied a positive times a positive, which then wouldn't have caused our middle term to cancel. So we would have had a trinomial instead of a binomial here to be factoring. Okay, so we are just make sure we're looking for differences. Okay, so here's one where we're running into a problem because 3 is not a perfect square. Okay, so we can't factor this quite like we did the other ones because that's an issue, right? 3 is 1 times 3, and that's our only option for factors, okay? But what we can do is we can go back to our knowledge about factoring out a GCF, and I can check, is there a GCF here? And yes, there is. We have a GCF of 3. So let's factor that out first, and then maybe we'll have a perfect square inside the parentheses. All right, so we're going to have 3 times a squared minus 9. Okay, so now I have a 3 on the outside, and inside my parentheses is again a nice perfect square. So I'm going to factor that. So I'm going to keep my 3 with me because remember at the end we want to multiply this all back out together in order to be able to get back to our original problem. So no dropping bits. Now I'm going to factor this. So a squared is really a times a. 9 is really 3 times 3. And to get that negative, I need one positive, one negative. So this is a two-step factoring piece here, Okay, so we just want to make sure that you're following through and you're always looking for that GCF.